first of all, I would like to say that I'm happy to be here to present some of our work, and I would also like to thank really the organizers for putting together such a nice program and such an interesting workshop. I will report some work on particles which are driven by feedback, and let me start just by some general words about what is feedback or what are we doing in feedback control. So the general idea is that we want to manipulate the dynamics of a system based on information from that system. And this is a concept which is traditionally was used in fields like robotics, for example, laser dynamics, for example, to control chaotic laser dynamics, or even satellites, macroscopic systems. But it's also used in to stabilize, for example, exotic states in quantum optics. So there are quite many areas of research nowadays, and here I'm giving two larger reviews on that. So more recently, people started to apply these concepts on colloidal systems, including active colloids. And just conceptually, so what you usually do is, if you are looking at a colloidal suspension, passive or active, the particles are relatively large, as we know, so they are excellent control targets, so to speak, the particle positions, and even the orientations are measurable. And then, and this is shown in these quite early experiments, you can, for example, use feedback control based on optical tweezers, where you manipulate the particle position. Now, an aspect which which is important in my talk concerns the fact that in many, not all, but many of these instances, you actually have a time lag between the collection of information, let's say the imaging of the particle position here, and response to that information. So in other words, we do have not an instantaneous feedback, but a feedback which involves a time lag or time delay, as we often say. And of course, you can have, let's say, fixed delay times or distribution of delay times. There are different variants of this, but the point is that in some, at least in some of these experiments, this cannot be totally neglected. And this is just one example. What I'm showing here. They set up from Lucio Iser's group in Zurich, where they actually looked at active particles and feedback control of their rotational dynamics. And I like to show this figure because you explicitly see that there's a delay, a time delay between or in monitoring the translational motion. Now, traditionally, these time lags, I forgot to say that these delays are, of course, also or can be important in biological systems and sensing, for example. But if you talk about feedback control, these time lags have often been seen more like a perturbation and something which is nasty, which you do not want to have. But they are actually also interesting examples where these time delays can actually have what I would call a constructive effect. And so you can actually use it. And I've given just 3 examples here. This list is not complete. So one example shown relatively early is coherence resonance. This occurs if you have particles in a double well potential, for example, bistable systems. And then noise and delay can constructively combine themselves to see resonance-like phenomena in the absence of any external force. So there's no stochastic resonance with an external force, but it's just driven by the interplay of noise and delay. More recently, there's very interesting work of Frank Tschicher's group, and Victor Holoubek was involved, and others as well, with active Janus particles, where it was shown that by using time-delayed control, you can actually create stable clusters of these particles. And then an example on which I will focus today, which we got interested in, concerns repulsive time-delayed feedback. And this is work together with my PhD student, Robin Kopp. What I will show in that context now in the next minutes is that, first of all, the dynamics itself, so that this repulsive time-delayed feedback can actually drive a particle, a passive particle. And then I will talk about some results from the perspective of stochastic thermodynamics, which is the main theme of this workshop. And if I have time, finally, a little bit about the collective behavior. Okay, so repulsive time-delayed feedback can be realized experimentally, for example, by repulsive optical traps. There's a nice experiment of the group of Wel-Dallens in the Netherlands. What they used is a combination of optical traps and a dumbbell particle. This is shown here with different refractive indices. And what happens is that this particle circles on a ring, and this red trap here, so to speak, pushes it on the ring. Yeah, so it's a repulsive trap, and this is an example of this setup. Also, more from the biological world, there's an interesting observation on cell migration on a viscoelastic substrate, where it has been shown if the cells move on the substrate, they actually deform it. And because of the deformation, and because the deformation occurs after the cells have been at some position on the substrate, there's actually effectively a driving force. So this is the situation we were interested in, and the model we were using is shown here. So we are looking at overdamped motion in 2 dimensions, and I'm first focusing on one particle. What I do here entirely through this talk is I'm taking kind of a coarse-grained perspective, I should say, because I'm not taking into account the full system of particle and bath and controller. Yeah. So rather what I do is I just assume that the particle is under the impact of a force which involves some sort of time delay. In that sense, it's coarse-grained, and I'm not taking into account all degrees of freedom. So what we have here is a force which derives from a repulsive Gaussian potential with a time delay. This is written here. So what you can imagine is that you have a particle here, and the force is kind of a Gaussian located at the particle's position at an earlier time. So this is not, even if we do not do thermodynamics, but just want to investigate the dynamics, it's not easy, because what we have here is now a Markovian or delay differential equation. Yeah. So you cannot do all the standard tricks, like, for example, going easily to a Fokker-Planck representation or so. And the other point is it's a nonlinear problem, and we will see that the nonlinear character of this force is actually important for the dynamics. So to get some idea, we first looked at the deterministic behavior, just a single particle. In the deterministic case, it turns out, if you look at the particle's velocity plotted as function of time, that there are different regimes. If that feedback strength, I'm going back here, this parameter here is rather small, and then basically nothing happens. I mean, in the limit a to 0, nothing happens. But if this a parameter is sufficiently large, then we can actually get a long time steady state where the particle assumes a constant finite velocity. And this is really an effect of the nonlinear feedback. If you had a linear repulsive feedback, this is this upper line here, the particle would so to speak, feel just an inverse parabolic trap, and the force would just increase all time, and then the velocity would just diverge. But if you have this nonlinear feedback, we find these long time stationary states. There is a condition for that, which will become important later. So feedback strength and delay time and range have to fulfill this condition to see this long time steady state. Yeah, so this is important, and it's really something which only occurs in the nonlinear case. So if you now add noise, we still see some traces of this long time finite velocity. So on the left-hand side, we just have trajectories which spread out the larger the feedback is. I'm now comparing feedback strength over KT. And if we look at the mean squared displacement, what we find in this feedback-driven case with noise is that it's diffusive at long times. So the direction randomizes, which makes sense. But at small and intermediate times, we have a combination of linear, of ballistic and diffusive motion. In other words, there is some sort of effective velocity and persistence even in the stochastic case. Yeah, and we can actually, I'm not going into details here, we have analyzed that by fitting these MSDs, these mean square displacements, to those of active Brownian particles, which have quite similar MSDs. And this helps us to calculate the effective velocity and also persistent time of this particle in the stochastic case. Yeah? And what you see, for example, if you look at the velocity, it's not that surprising. If we increase feedback strength over kT, this effective velocity increases. There's no effective velocity at very small feedback, so there is a threshold behavior. What we also find is that even in the stochastic case, the deterministic limit is useful because it gives us a good estimate. These are the solid lines of the effective velocity. So to summarize, what we find is that these nonlinear time-delayed feedback acts as some sort of propulsion mechanism similar to what we see, or maybe comparable to what we see in an active particle. So what we're interested now, and this is what I wanted to show you today, is are there, or what the question we were asking is, do we see this onset of persistent motion of a particle in thermodynamic quantities? Yeah, because we do have this threshold, and the question is, can we see something from the perspective of stochastic thermodynamics? And of course, there is very substantial fundamental work on stochastic thermodynamics of these time-delayed systems. People have looked at things like second law and fluctuation theorems. There's lots of work of Martin Rosenberg, and particularly on underdamped systems and on the question how you define the total entropy production in these systems. We have later done, together with Sarah Loos, a series of works on overdamped systems, focusing on different quantities, and also in this work of Katka, they have looked at entropy production. But one should stress it's really a delicate issue because of the non-Markovian nature of the dynamics. And also many of these works are looking at linear systems. So what can we do for this nonlinear problem at hand? And what we are focused on is the average heat production rate, which Thomas already introduced in his work, or dissipated heat. This expression here, again, is taken from Sekimoto's book, for example. And if you now plug in our Langevin equation, we get this one here. And the result, or the data I'm showing here, are just numerical data, yeah, for this long time dissipated heat as function of feedback strengths. What we see is, yeah, what I'm showing here, this vertical dashed line marks the onset of persistent motion in the deterministic case. Okay, what do we see generally is maybe not so spectacular. There is dissipated heat for all feedback strengths. In other words, although there's no additional driving force, we always have dissipated heat. Yeah, or in other words, the delay alone produces or brings these values here, which is not that surprising if you have looked at other feedback-driven particles where people see the same, that delay already induces non-zero heat production rates. What we also see is, and this we found more intriguing, is that this Q dot, this heat dissipation, is non-zero already below the threshold to persistent motion. So there's no really measurable velocity, but still we get this non-zero heat production. If, on the other hand, we go to large feedback strengths, then you see that the numerical data are well described by the solid line. And the solid line is nothing else than the heat production in a system driven by a constant force, or a particle moving with a constant velocity. So that means above this threshold, we can essentially just look at this particle as a particle going with a constant velocity or driven by a constant force. That's not so, maybe not so surprising. As I said, the more difficult regime is this one here. So can you somehow understand what's going on for weak feedback? And so the first idea one would have is, okay, try to linearize the system. This is written here because then we can directly express this heat dissipation by this expression. So we essentially look at the displacement, which looks straightforward. We are now in a linear delayed system. And for linear delayed system, there's lots of results from the mathematics literature. However, there's a problem because of these prefactors here. In fact, it turns out that this particular differential equation is only marginally stable. Yeah, this has been analyzed. And so if you have more general prefactors as written here, this K1 and K2, you can immediately calculate these heat dissipation. But with the problem at hand, we are, so to speak, at the boundary of this stability region in the linear case. It turns out, fortunately, that we do get a stable result, even with noise, if our feedback parameters are below this threshold of persistent motion. And this is why we get results there anyway. Yeah, so this explains why we do get stable results in this regime. So let's briefly compare linear and nonlinear cases for small feedback for this heat production rate. So what we generally found is that the linear system gives the trend correctly, but if we look at values, we see that it overestimates these heat production rates in the nonlinear case. The reason being, linear case means we have this inverse parabolic, which gives much larger forces than our actual repulsive Gaussian. So what happens now if we approach the threshold? Again, there's a large difference between linear and nonlinear feedback. In the linear case, I'm sorry for this data here, we see actually a divergence of this Q dot here as function of delay time, but not in the nonlinear case. And maybe I was asking before, do we see any indication of the onset of persistent motion in these average heat production rate or in other thermodynamic quantities? Where you actually see something is if we plot this quantity as function of delay time there, and this is shown in the left plot, we actually have we actually see a maximum close above the threshold of persistent motion. And this corresponds to a velocity maximum, which we see already in the deterministic system, and which just comes from the fact, again, that we have a nonlinear potential and therefore also a non-monotonic dependence on this delay time. Okay, this is basically what we have for this average heat production rate. We also started to look at distribution functions, which shows some interesting results as well. But I see that our chairman already gives me a sign. Maybe just as a last point, one reason we were interested in really getting this dissipation in this feedback-driven system is that these particles also show quite interesting collective behavior. Namely, what we found, and I'm just showing one simulation snapshot here. So we now have many of these particles at a large density. This is the left upper corner. If we now switch on this time-delayed feedback, we find under suitable conditions something like a flocking state. So the question is, there is not only an onset of persistent motion on the individual particle level, but also coherent motion collectively. And we were interested in do we actually see something in this heat dissipation, for example, if we cross this transition to coherent motion? And these are just some preliminary data we have. It actually turns out that we do not see much, yeah. If we plot this heat dissipation as function of the feedback strength over KT, these are data for different densities, and all of these values here lie in the regime of coherent motion. Yeah, but as you can see, there's nothing spectacular going on, and this is kind of interesting in the light of other recent work on dissipation in active systems with polar or velocity ordering. So this is something which we are currently trying to better understand. Yeah, but yeah, to understand really this collective behavior, it's of course crucial to first understand the single particle behavior, which is yeah, basically why I discussed the first point. Thank you very much. Yeah, if there are questions, I'm happy to answer it.